Hello and welcome to the lectures Large Language Model Part 1. In this lecture, we are going to understand what do we mean by large language model. Then we start discussing on LLM architectures, loss function, and then the tokenization. Then we summarize by understanding the different tasks of the large language model. Now we start with language model. A language model is a system that learns the patterns of the language and can predict or generate text. That means it essentially estimates the probability of the sequence of words. Now we take an example and try to find out what this means. Now a probability distribution over a sequence, let's say a sequence of or a sentence, the sun rises at the east. What is the probability of this sentence? So in language model, this represent the probability of the entire sentence. And how we are going to model it or to find out this? That you can see it is a joint probability here. So it is P of x multiply P x2 given x1, P x3 given x1, x2 and so on. That means for this particular sentence that sun, the P of sun multiply rises, this particular one given the sun, then multiply at given sun rises, then probability of the sun rises at, and what is the probability last? The east sun rises at. This is the given. That all probability we multiply, you get this. That's why this language model in nature is autoregressive models. And this is done by general. Okay. So as a whole, that we understand, the model can predict the next token or next word given the past context. So this is the context. So based on this past occurrence of the words, what we essentially call the context, this kind of language model is going to predict this. This is the main essentiality of the language model. Now what we can understand here, that language model is a system that learns patterns of the language and can predict or generate text. So it understands the context to predict the next token or next word, while it is basically estimate the probability of the sequence of word or enter sentence. Okay. So what we have seen, a language model is a statistical model which can predict the probability of a sentence or part of a sentence. For example, another example, where if we say that what is the probability of I'm a good boy. Now this sentence syntactically or semantically correct. Syntactically means grammatically it's correct, and some hold some sense or making some sense. That's why this probability is high. But you can see the good am I a boy, if this kind of sentence has been given, probability is low because this is grammatically wrong. So as we said that this autoregressive model is basically going to, that is a similar thing kind of, that I then is the first word or first element of this sequence. Then given I, what is the probability of am? Then given I am, what is the probability of A? Then given I am A, what is the probability good? And given the probability of I am A, the probability of the boy, and you multiplied all these condition probabilities, so we can get the probability of the full sentence. That we have seen. This is another example. So this is actually the language model is doing. Now there is a autoregressive language model. That why it is called autoregressive. Now here what we have seen, that this language model, why it is autoregressive, because that it basically taken some part of the already seeing tokens to predict the next tokens. That's why it's auto-regressive. So what are the basic steps of this autoregressive language model? Let first is tokenize. We'll see it later in details, but here we just a very brief overview of this. So tokenization means basically that we have to find out, given a sentence, for every action there is equal and opposite reaction, whatever this is big sentence. Now tokenization means first splitting the words, and then it assigns some values to the corresponding element of the sequence. Here the word of the sequence. So tokenization is this. Basically these are the tokens. Now it's some values. Now given the set of tokens or a sequential set of tokens, what with the probability of the next token to be generated. So now if you had find out for every action there is an, so this part, this is the existing whatever we have already seen. What is the next token X? That is done by language. And this language model actually samples some corresponding words. It may be dual, maybe equal, every action, whatever. And then we'll find out some of them, detokenize and predicted output will be equal. So this is the entire story of this autoregressive language model. This kind of thing. So major 4 steps: tokenize, predict the next token using the previous tokens, something, and detokenize. Now, what do we mean large language model? What is the basic topic of this today's discussion? So it is basically same thing that what language model is doing. Given a set of tokens or a set of words in a sentence, find the next word or next token. Now this thing we call prompting. This part is called prompts. So we usually train a neural network to predict these probabilities. Okay, so for this conditional probability, we doing it by training. A neural network trained on a large corpora of text, and that's why from comes this particular word large. This neural network is a huge text corpora, and that's why it's called or known as the large language model. So that is the basic idea. The language model which has been trained on a large corpora of the text called the language model. Okay. Now we are going to understand the large language model in depth. So basically we are going to discuss some major points. We start with architecture and then loss function, training algorithm, fine tuning, etc. So first what we'll see here, this is the transformer architecture, this is the encoder model, and this is the decoder model. Basically, large language model generally use a series of encoder or series of decoder. We'll see some models use only encoder, that is encoder only model. Some models only decoder, is called decoder only model, and some both encoder decoder. We'll see each of them. Okay, so let's start this. So three major architectures for this large language model. One is encoder only model, that is basically BART family, BART kind of model, where you can see that the bidirectional context are used. Then the decoder only model, when only transformer decoder used, and this is, you can see this is unidirectional kind of thing. Okay, that GPT, Claude, Llama, these are the major models. And this is a encoder decoder model, both these encoder as well as decoder is involved. 95 whisper, these are the basic model. It's basically used for this machine translation, a sentence in one language to another language, something like that. This decoder only model is for basically the next token prediction kind of. Encoder only is generally classification kind of task. So this is the basic architectures. So we'll see one by one what. So we first start with encoder only model. This is the masked language model that will see that how actually it being trained. Some of the tokens are randomly masked, or there is some way to masking this particular tokens, and then the model trained by predicting this masked token. This is generally the BART family, really is one of the major model under this category. So it used bidirectional attention. You can see this from these arrows that attention is meant, meaning they consider both left and right context simultaneously. So basically this sentence is bidirectional. So and then once it be trained, then it is fine-tuned to the particular classification task. So it may be trained on the supervised data. So this data may be a very less. So what is the basic purpose? That is the two major thing we'll see later when the training comes. That we pretend this data based on basically this pretending done unsupervised way. Okay. After that, for a given task, that it is been trained on a small amount of data for a particular specific task. This is called supervised fine tuning. Okay, so this is the encoder only model. The next comes is encoder decoder model. Encoder decoder models combine the strengths of both encoding and the understanding of the sentence and the decoding of generation of this. So it is basically the understanding part and this is the generative part. So they are basically designed for tasks where transform one sequence to another. So this is a kind of machine translation. So machine translation, speech recognition, this kind of model are very much. Okay. Next, another very important model that is called decoder only model. A decoder only transformer model is a type of transformer architecture that uses only the decoder part of the transformer to process input and generate text. It is autoregressive in nature, as you can see from here, that these models are designed primarily for autoregressive language modeling, meaning they generate text one token at a time by predicting the next token based on the previous tokens. That you can see here. First token is generated almost independently. Then these tokens are generated from this and this, and this is basically this, and so on. So this is basically the decoder. General is basically the GPT like of applications. Basically depends on. So these are the basic three kind of models, that encoder only, decoder only, and encoder decoder models. Now we are going to understand how a language model, or basically this autoregressive language model, works. Now there is a given sentence. Now sentence is basically some words of a given sentence, not full all words. What is the job of this model? That given these words, since it is autoregressive, what will be the next word? So given this all these tokens, what will be the next tokens? So for every action there is an, maybe for this particular sentence there is equal. What is the first step? It is basically tokenized. Tokenized mean that what we have seen, that is some numerical representation. So next we'll see that is a word embedding, that is and positional encoding, that also we have seen before. this kind of things will be done, and then it come to the neural net. This neural net is essentially a transformer. Now this transformer take these tokens and find a context out of these tokens. So that is very important to understand what is the role of the input is this sequence of words or sequence of tokens and finding a context vector. Now this context vector is fit to the linear layer. This linear layer what will take this context and some kind of probabilities or some values. Now what there is one thing that we have to very important understand. This mapping from context vector to this. Now this is, if let's say context vector is a d-dimensional, small d-dimensional. It is to the norm of this V. What is V? Is the vocabulary size. So what is mean by vocabulary? Vocabulary is basically there is how many words is possible in this particular sentence or a group of sentence. So for English text it's maybe very big, a lot of words. So here also similar. So this is the vocabulary size. So what will be the basic this vocabulary, and for each word some values. They put the softmax and get the probability values. Okay, and based from these probability values we find something which is most probable. Okay, so that is basically the whole story, where from a given set of words or a sequence of tokens, they find the context and based on this put the next token or next word and then this probability of this and the highest probability choose. And since this is been basically that initially we know when they are pretending, so they know this word, this particular sentence, that for every action there is an equal and opposite reaction. This is very famous Newton's third law. And so based on this sentence this will generate the total formulation, a total model is being trained based on this. Okay, and then it will basically find out the next token. Okay, so for every action there is a what, this is the probability, that is for all the these tokens under this vocabulary. Next we are going to understand what is the loss function of this large language model training procedure. As we have seen that the model is going to predict a particular word or a token given the previous words. Now for this particular sentence, this for every action there is an opposite reaction or something like that, that this thing that for and every is already we have seen, and based on these tokens or these words we have to predict the third word or the next word. So basically this is the model prediction is this, that there is action, okay? And definitely there is some targets because we know the sentence before. So that means this is kind of the way it is being trained. So if we know the target that this will be the action, so we have to find out that this probability should be high other than these values, because what we are going to choose, that was the highest probability. Okay, so we consider a cross entropy loss between the model prediction and the target value. So what is basically this loss? We have to increase this and decrease this, so that what we can understand that this probability value will be higher and other probability values lower than this, so that that will be the maximized. So that is basically how the loss is being generated. So minus log of p of action, action means this particular word or token, should be minimized. Is minus, so plus is maximized. So that means the probability of this maximized, so negative is minimized. So minus log. So that is the way this loss function of this kind of autoregressive neural language model is being formed or framed. So this is the cross entropy loss, and then what we maximize the text log likelihood by this way, that this is the it's going to maximize this, and then we have to maximize this, then we have to minimize this particular thing. So this, because this is a maximization, so it's a minimization of negative of this, and these are the same things. Basically we have to put the summation because we put the log this. So it is a minimum of this. So log is loss is basically this particular function. So minus summation of log of p xi given x is equal to I minus 1 to I minus 1. So that means this, that given these two, that this sequence of tokens or this sequence of what is the probability of this action, and that we are that likelihood we are going to maximize to action. So that is the basic idea of the loss of this setup. Okay, so we have to remember this, that maximize the text log likelihood. This log likelihood is basically this, because this is basically that the autoregressive kind of modeling. At 1 to I minus 1 we know. Knowing this, what is the probability of xi? So 1 to I minus 1, this, that 1 2 we know, what is that? Exactly this, the same thing. Okay, fine. Now we are going to find out what is the other. This is training. This is the loss function we have seen. Now, so training algorithm, there is a things. So in this particular lecture we used the tokenization. Then we will see later things in the next lecture. So in tokenization, what we are basically going to see or understand by this statement, that a tokenizer of a large language model converts raw text into tokens. First you have to understand. What do you mean by tokens? The smaller unit such as word, subword or characters that the model can process numerically. So tokenization is basically two steps. One is it first, that is tokenized kind of thing. They divide in a smaller unit. What will be the unit? Maybe word, maybe subword, maybe characters. And then for every this smaller unit, that they basically assign some numerical values. Okay, so these tokens are then mapped to IDs, that means values that a neural network understands. Now, first of all, why it is important? Now, it is more general than words, because in words there may be typos, but there is this kind of things when we tokenize it. Just for example, there is some vocabulary. For every possible word, there is some sort of tokens. So when we tokenize this kind of mistakes, there will be no matching tokens for that. And you can understand that there is some typos. Another thing, tokenization at a different level, maybe in character level, more fine-tuned, on word level, sub-word level, etc., in a different level of granularity, helps language model to learn meaning or context of the sentence at a different level of abstraction. That is very important to understand. At character level, we know that it's a very small thing, a very less context. But when we go to the sub-words, some higher thing, another word, so the semantic information, or you can say contextual information, is being increasing, and how if we do the different level of granularity. Higher the granularity, more the contextual information. So this kind of things, different level of abstraction, is helps to language model to learn meaning or context in sentence at different levels. So the butterfly is amazing. This is a sentence. Now when you put the character level tokenization, it is every character, T, H, E, B, U, T, T, E, R, F, L, Y. Now if you see, then these characters, and the full stop is also the punctuation marks kind of thing. Now these things, that is the character level. If you take a histogram of it, that what we'll see, that how many such characters and how many times it has been occurred in this. And what is the vocabulary of this? The English characters and punctuation marks and something similar kind of thing. So that is very interesting here. Okay. So it is a character level tokenization, is much simpler. But if you go to the word level tokenization, so the is one, then butterfly is another, is amazing. These are the different words. Now one thing you have to think, if you see the vocabulary, the entire English words vocabulary is not huge. Sub-word level tokenization, the butterfly is amazing. These are some words that somewhat mean. So this is sub-word level tokenization. So tokenization is basically a kind of way that we divide this particular sentence in a different level of granularity to understand the sentence at different level of abstraction. That's the meaning of the tokenization. Now, what we kind of token as a common subsequence. For example, with say byte pair encoding, that basically used by this GPT. Now, what is the training step? Now, it is not the training of the LLM. Please, this is the training of this byte pair encoding. So they take a large corpus of the text and start with one token per character. Okay. So one token per character is basically. Okay. So what's in the training corpus is merge common pairs of tokens into the one token. Okay. Now repeat until this desired vocabulary size are all merged. Okay. So how we basically, so example, words in the training corpus: low, lower, newest, widest. These are the possible words. So now represent each word. These are the characters plus end of word marker. So low word is LOW and then end. So lower is blue. Then newest, this the basic first representation, and wildest. So this is the way we. Now we have to count the frequency of adjacent symbol pairs. So LO, this is the first. then OW is LO and OW, then W and end of the word marker, and so on. WE, because LW is LO is already there, so WE. OW is also there, so WE, then ER, NE, EW, ES, ST, and so on. So this is the count of frequency of the adjacent symbol pairs. Okay. Now then we merge most frequent pairs. That you can say how many there is a ES here. Now here you can see that this is ES, this is ES. So on these two things is highest. So we can put it where E is equal to E plus S ES. So it is now low, this end of word, lower end of word, new ES, now it is merged, and widest ES is merged. Now next merging is what? We continue merging next frequency pair L plus O. This is LO. And there is EST. So LO is a pair, EST is a pair. In this way we are keep on merging. So if you do in this way, we can find the final vocabulary of this. L, O, W, LO, LOW, EST, ER, WID, NE. So these are the final vocabulary for this after many merges. And then according to this vocabulary, if this subword tokens, lower is low plus lower, newest is new is newest, widest is wide. So this is the way this byte pair encoding, given this kind of, but how we basically make this vocabulary. This is the corpus, this is the corpus, and accordingly we use the subwords. So this is a meant, take the large corpus of the text, something like that. Start with one token per character, that we will basically train here, and merge common pairs of token into one token, that to this, and keep on merging, repeat until desired vocabulary size are all merged. So what is the advantage? It handles the unknown words very well, keeps the vocabulary small and captures the common words. So this is called the byte pair encoding. Now, what are the basic tasks of this large language model? So large language model works by assigning probabilities to the sequence of words and predicting what word is the most likely to come next in the sentence. That we have seen. So during training, the model is exposed to a massive amount of text and learns to guess the next word based on the words that came before it. Then this process is called next token prediction. That given a set of tokens, what will be the next token? And when generating text, the model produces the output by sampling from the possible new words according to their predicted probabilities, and then repeating the process for each subsequent. That when they are basically produce the output, that there will be some, what we can see here. Here what we have seen, that they will produce a probability of this. And which will be the maximum probability? That we basically. So here essentially the kind of summarization of this. Although the training objective is simply to predict the next word. The model ends up learning a large amount of linguistic and factual knowledge from the data it was trained on. Now first, this is a very important statement. Our training object is simply to predict the next word given, but by doing so, this model ends up learning a large amount of linguistic as well as the factual knowledge from the data it was trained on. So it is not only learning the next word to be predicted. At the same time, this kind of linguistic and factual knowledge. And by seeing the pattern across the huge text dataset, modern models like GPT-4 or Llama develop an understanding of grammar, context, relationship between concepts, enabling them to generate a coherent and meaningful text. And that's why it's a so powerful generative model. Because they are trained with a huge corpus. The way it is being trained is very simple. That's just next token prediction. Given a set of tokens, what is the next word? But by doing so, it basically try to understand, or it understands the linguistic and factual knowledge from that text trained on. And that is the major understanding of the large language model. That's the major task that has been done, and by doing so, it acquired this kind of knowledge. And that makes this large language model very powerful, a generative model. So in this lecture, what we have understood, that we first introduce this large language model, then we try to understand what is the language model, and then what is the large language model. Then in very briefly we know what are the LLM architectures, just some of them, that's encoder only, decoder only, encoder decoder model. Then what is the loss function and token. Then we summarize the task of this in the next lecture at how it is being trained and what the other aspect of this. So next we start part 2. Thank you.